क्या दिख रहा हूँ? ऐसा दिख रहा हूँ? कैमरा थोड़ा ऊपर कर लेता हूँ। way. ओके आ रहा है इधर हैंड पिक हैविंग हैंड पिक ओके प्रीतम मंडल चैटिंग सो ये स्टीमलेस पे लिखेगा ना हाँ इट्स ओनली शोन इन स्टीमलेस not other else only स्टीमलेस it will showing okay let me okay so it's showing if I do gesture it is showing or not no it's not showing this not showing only showing the chattings if I try this it will show why not it's shown here has show face red droppy eyes face red droppy eyes face red droppy okay we are listening web how we are listening web okay. Get your stream title and description okay now start the productivity is meta-analysis pure okay meta-analysis pure NCERT book first we have to watch the videos then we will be reading the NCERTs and if we get something confusions then ask about chat GPT to help us to understand first solution suspension and collate what are the difference
which also means thinking we can categorize them as heterogeneous and
what is the
homogeneous
difference now
mixtures.
I'm
Now, what if I tell
muting my
you that the
mic
first mixture, well, this one is homogeneous, salt is easily dissolved in water, and the other two are actually heterogeneous mixtures. We can see why chalk would be a heterogeneous mixture, but why is milk a heterogeneous mixture? We will talk about all of this, and in doing so, we will understand the differences between a solution, a suspension, and a colloid. So, to begin with, let's dive deep into a solution. All right, to begin with, we will talk about solutions, and as an example, we will take salt water. Now, the first characteristic of a solution is that it's a homogeneous mixture, which also means that the solute, in this case the salt, it's evenly or uniformly distributed across the body of the water. It is dissolved in water. And what does that really mean though? So let's think about it. So let's say there are these water molecules or ions. Each dot represents a water molecule, right? H2O molecule. So when we say that salt is dissolved in water, it means that each individual particle or ion of a salt, it is spread out uniformly across the body of the water. So this is one individual, this is one individual particle or ion of a salt, one individual particle of, let's say, NaCl, right? Each particle of NaCl of salt is taking up the space between the water particles. So that is what it means when we say something is dissolved in something else, in this case salt into water. So this is the first characteristic of solutions. The other is, we can say that the particle size, in this case the particles that are dissolved, they are extremely small. So this one individual particle, it's of the order of 0.01 to 1 nanometers. Now third characteristic is that particles don't settle down. If you have a salt water solution and you let it be for some time, you will not see salt settling down near the bottom of the beaker, which means that you cannot really separate salt from water by filtration. If it is not settling down, then how can you separate these two from each other? So it can't be separated by filtration. One more characteristic is that the particles don't scatter light. What does this mean? So let's say if we have a laser and we strike laser onto this glass full of salt water solution, you will see the laser light striking the glass at this point. You will see it coming out from this point, but you will not see the path of the light inside the salt water solution. And that is what it means when we say that particles don't scatter light. That is, you will learn about this in detail in other videos. So when there is a particle, let's show a particle with some other color. So let's say if there is a particle right over here and there is a laser light coming onto it, the particles are so small, these particles are so small, they are so small in size that this light just keeps on going, it does not get scattered. And we will see when does it get scattered under suspensions and colloids, but in this case it is not scattering. So this was all about solutions. Now let's move on to suspension. Alright, so for suspensions we have the mixture of chalk and water. The first characteristic of this mixture is that it is a heterogeneous mixture, which means that the particles are not uniformly distributed across water. You can easily look at them even. So from this very property, you can say that when you just let the mixture be for some time, these chalk particles will settle down near the bottom of the glass, and you can also separate them by filtration, right? So some other properties that we can attribute to suspensions, one of them is that particle size is greater than 1000 nanometers. That particles separate on standing. This chalk will settle down, which means you can separate them by filtration. And finally we can say that particles scatter light, which means if there's a particle like this, so the particle size is quite high in this one, right? If there's a particle size like this and there is light coming in striking the particle, it scatters in all the directions, right? So there could be some light that is coming to you, and these could be those rays coming into your eyes. So what that means is, if you have a laser light striking this mixture, then you can see the path of the light inside that mixture. Alright, now let's move on to colloids. So here we have colloid, this is milk. Now the first property is that it is a heterogeneous mixture. Now even though the particles in a colloid, they are uniformly distributed, so let me write that, they are uniformly distributed, even then this is a heterogeneous mixture. Even then this is a heterogeneous mixture. And let's see why that is. So if you think about the size of the particle in a colloid, that is between the size of the particle in a solution and a suspension. This is 1 to 1000 nanometers. It was much smaller in a solution and it was greater than 1000 nanometers for a suspension. The particle size is in between. So what that means is, we say that a mixture is homogeneous when the solute is uniformly distributed. So that means if there are solvent particles like this, let's say if this is water, then each and every individual solute particle will take some space in between these solvent particles. So if there is salt dissolved in water, you will have one individual salt ion or particle taking up the space in between these water molecules. That is what it means when we say something is dissolved, right? In a suspension, something is different. So in a suspension, if there is these water molecules, then chalk, that we took the example of chalk, you will have clumps of chalk, but they're not taking up the space in between the water molecules. You have like a clump of molecules, not an individual molecule, right? And for a colloid, things lie somewhere in between. So the particles are not as large as the particles in a suspension, but also not as small as the particles in a solution. In a colloid, if you have these water, something like this, solvent molecules or water molecule, then the particles are not individually taking up space in between these solvent molecules, but also they are not as large as the suspension particles. These are still very tiny blobs or clumps of particles, but they are not entirely dissolved in the solvent, right? For something to be dissolved, individual ions or particles need to take up the space in between the solvent particles. That is not the case with colloids. Neither is that the case with suspensions. But because the particles are much smaller than the particles in a suspension, these particles remain suspended. The colloid particles, they remain suspended and uniformly distributed. So in the case of milk, you have these liquid droplets of fat. I'm showing fat with blue droplets. You have these liquid droplets of fat uniformly distributed across the body of the milk, but they aren't dissolved, they are just suspended in milk. So we can also say that particles, they don't separate on standing, they remain suspended, which means they cannot be separated by filtration, right? And the last characteristic of a colloid is that particles, they do scatter light, and in fact that is called a Tyndall effect. So when you strike a laser across the two ends of a glass, you will see the path of the laser light through milk. That is because when light strikes a particle of a colloid, it scatters the light in all the directions. This effect is called a Tyndall effect. Alright, so these were the differences between suspensions, colloids, and solutions.
So we understand about what is collision, what is colloid, what is suspension, what is solution. The solutions notes, there is notes. This note, one pad, there is one pad, one note, sorry. So it's saying that where is it? Hmm. It's showing, so they are basically saying that three glasses, I'm drawing here, sorry for the inconvenient drawing, but just have to understand it. So three glasses, so one is water, three glasses of water, here. No, not all water, two glasses of water. So this is H2O, this is H2O. So if I adding one spoon one spoon of one spoon of NaCl, then 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 the water will be here is a solvent and NaCl is solute. Oh, sorry, अरे यार, it will be solute, and you already know that which is lesser represent in the solution, we call it a solute. So in this mixture solute and solvent mixture, we hardly recognize in water salt, we hardly many efforts, we hardly after the filtration we cannot filter the salt when you do filtration. Only when we When we evaporate the water, then we can find the salts only that way. So this is very small, like you can say it is less than 1 nm, less than 1 m. It's the solutions less than 1 mm, less than 1 mm size solutions. You can guess it, that you cannot see it naked eyes, or you cannot see the naked eyes the solution, or if you pass a light from it, it will clearly. So if you pass from this, if you pass a light from it, it will clearly pass directly, no other thing will affect it. But in this, what is this? This is cloud. Clouds are basically, it's bigger than, it's bigger than 1 mm, but it's lesser 1000 mm. So it's basically between. Examples are cloud. We can say milk is a cloud. Milk and other mixtures like milk, other mixtures like milk is a cloud and other things. So milk has many properties in it, like fats, calcium, magnesium, or etc. But when you pass a light from it, you can see a effect is showing. What effect? Effect means when you pass a light, that it will reflect. Sometimes it will not clearly beyond that can directly go that, but it will reflect. That's why we called cloud, and clouds are shown effect. That effect we call it a Tyndall effect. Only clouds are show Tyndall effect. So you will show the a reflection happening here. So that's we call Tyndall effect. So only clouds are shown Tyndall effect. Tyndall effect. Clouds are so. And the last one is called suspension. Last one called is suspension. Suspension is basically those mixtures like chalk in water, mud in water, that we can see in our naked eyes. Obviously, chalk in water, chalk plus H2O, chalk in water, mud, mud in water. This is called suspension. We can see our naked eyes, and these solutions we can say is bigger or less. It's bigger than 1000 mm. It's bigger than 1000 mm. That's why I call it a suspension. You can see our naked eyes. Got it? Now let's continue the video. I'll stop here.
Check out this cool experiment. I'm shining my laser light through 2 glasses of distilled water. To this glass, I've already added some sugar and stirred it very nicely so it's dissolved. To this glass, I have not added anything. Notice that we don't see the beam or the path of light in either of the glasses.
But now we'll go ahead and add some milk to the second glass. And notice what happens. As we stir that milk, we can now see the path of light. So the question is, why do we see the path of light when we add milk, but we don't see it when we add sugar to it? So the reason we get to see the path of light in this milk-water mixture is due to a phenomenon called scattering of light. So scattering of light. So let's see what happens. When we add milk over here, the milk particles get completely dispersed throughout the medium. They distribute themselves throughout water. And now when light enters into this mixture, it hits one of these particles. So let's draw that over here. So here's our light. Let's say this is the light from the laser. It enters into this mixture and hits one of these milk particles. So here's one of that milk particles. What happens after this is the milk particle reflects this light in all the directions. So it reflects light in all the directions. And the important thing to note over here is earlier we have seen that big objects like mirrors or a ball or any big object, if you take, they will reflect light in a specific direction. But turns out that when you get to these really tiny particles, they will always reflect light in all the directions. And if you're wondering why this happens, then it turns out we need to really dig into this deeper and figure out how light interacts with matter and everything, which will not do. So we'll just accept that tiny particles, this is a property of tiny particles. They will always reflect light in all directions. It's just that when these tiny particles get together to form a large object like the mirror or any other day-to-day life object that we encounter, then they only tend to reflect light in a specific direction. Okay, so this phenomenon of reflecting light in all directions is what we call the scattering of light. And because of this, some of the light is also reflected towards us. We are somewhere over here that we can't, I can't draw that over here. We are somewhere over here, right? That's where the camera is. So some of the light gets reflected towards us or into the camera. And as a result, that particle, we see that particle glowing red in color. It glows red because it's reflecting red. And therefore, that particle which it hit over here, that particular particle glows red. And then of course, not all the light gets reflected. Some of the light goes through as well. Actually, most of the light goes through. Let's draw that. So most of the light goes through. This is the light that didn't get scattered. Got that? This is the scattered light, and this is the light that didn't get scattered. So most of the light goes through, and then it hits another particle, and then again scatters off from that. So another particle over here will glow, and the same process continues, and as a result, all the particles which are in the path of that light end up glowing. And since these particles are really, really tiny, of course I've drawn them to be pretty big over here, but they are really, really tiny, and there are so many of them that when we look at it, we don't get to see the individual particles, but all we see is a straight line. So we see a line that is glowing, and that line is what we perceive as the beam of light. That's that beam that we're seeing. So what we are actually seeing are the milk particles who are scattering light, and as a result, they're glowing. And that's what shows the path of light. But why don't we see the path of light in a sugar solution? Don't they scatter light? Well, they too scatter light. In fact, all particles tend to scatter light. But here's the thing. It turns out that if we do the analysis, it turns out that the amount of light that they scatter depends on the size of the particle. As the particle size become bigger and bigger, they tend to scatter.
So here he is saying, right? So I told you that here he is saying about size, particle size. So I have told you that in sugar, if you dissolve sugar in water or salt in water, then the particle size is very small, very small. That's why the reflect is very small. We cannot see it in our naked eyes, but in colloids we can see it because the particles are 1000 nm to 1 nm between them. That's why we can see the reflection. That's why scattering. That's why we called it scattering light, also call it Tyndall effect. Let's continue the video. And
scatter more and more light. If the particle size becomes too small, then they do scatter light, but that scattered light will be so insignificant that we won't be able to see it. So considerable amount of light will not reach our camera. And that's what's happening over here. The particles in the sugar solution are so tiny that the scattered light is negligible, and that's why we can't see it. And in fact, analysis shows that if the particle size is roughly, if the size of the particle is roughly smaller than 1 nanometer, all right, this is not an exact value, it's a rough value. If particle size get any smaller than a nanometer, then their scattering effect is so tiny that when you shine light through it, we won't be able to see anything. And that's what happens in any solution. So you take sugar solution or you take salt solution, whenever something dissolves, those particles usually tend to be smaller than a nanometer, and that's why we don't see the path of light. But milk particles are way bigger than a nanometer. They could be about, I don't know, maybe, I don't know the exact value, but maybe around 60, 70 to 100 nanometers in size. On the other hand, if the particles become too large, so let's say we have particles which are too large, and again, a rough value would be, let's say they're about larger than about 1000 nanometers. If they get too big, then also we have a problem. Their problem is not with scattering. These particles can scatter light even more strongly because they are big particles. And by the way, an example of this would be dust particles. And you may have seen that sometimes when it's dusty and you're outside, it's nighttime, and there are vehicles with their headlights, you can see the beam of the headlight, right? That's an example of scattering of light by big particles, like dust particles. So they don't have a problem with scattering light. But their problem is, since they are too big, they tend to usually settle down due to gravity. So if we were to add dust to water, which we will do in a minute, we'll look at that in a minute, then even if you stir it very nicely, those dust particles will not stay long in the water through the bulk of the water. They will usually tend to settle down. And once they settle down, then most of the particles won't be in the path of light. And that's the reason they won't scatter light. So the ideal case for us to see a path of light would be to have particles whose size is somewhere in between this. So if we have particles which are not too small, their size is larger than a nanometer, but they're not too big so that they would settle down. They're smaller than, let's say, about 1000 nanometer. And by the way, remember, these are rough values, okay? Then we will get to see the path of light. And such cases, such mixtures are called colloids. So, okay, it's a little hard to see. So let me write that down over here. So it's called colloids. And you may have already studied about colloids in chemistry, the same colloids we're talking about. So colloids are the best example to see the path of light. These are called as solutions. Solutions are one of the worst to see the path of light because the particles are very tiny. Sugar solution, salt solution are examples of this. And these are called suspensions. They too scatter light very strongly, but the problem is they tend to settle down and usually not be found in the path of light. So if we go back to our experiment where the sugar solution is not showing us the path of light, if we look at it carefully, you can sort of see the beam, isn't it? Now this is not due to the sugar solution, don't worry. If we zoom in carefully, we can actually find the particles which are scattering light. You can see there are some dust particles that got also added when I added the sugar and some impurities. These are the particles which are larger than the 1000 nanometer size. So that is causing a suspension. So the scattering that we are seeing over here is due to these suspended impurities. And by the way, look at this dust particle which you can see over here. That is so large, we can even see it with our eyes directly. And as it swirls and comes into the path of light, notice how strongly it scatters light, okay? Just concentrate on this particle. Let's go back a little bit. Just concentrate on that particle. Here it is. Look at that. Look at that. Do you see it? See how strongly it scatters light. So big particles can scatter light, no problem. But their problem is that they tend to settle down. So most of those particles will not be found in the path of the light. And as a result, their scattering or their path is not so strong. It's nothing compared to what we see in colloids. So colloids are the ideal place to see this effect. So that's pretty much it. One last detail is whenever we have scattering of light due to colloidal particles, due to colloids, we often call that as the Tyndall effect. So scattering of light due to colloids is called Tyndall scattering or Tyndall effect because this guy John Tyndall did a lot of work on this subject. And this also has a great application. Tomorrow if we have any mixture and we want to know whether it's a colloid or not, we will just shine light through it. If we can see the path of light, that's Tyndall effect, then it's a colloid.
What does fog or mist, a sponge or butter have in common? Well, it's difficult to tell that, right? Well, it turns out all of these substances, they are colloids. But they are so different from each other, right? So does that mean that there are some types of colloids? Well, it turns out yes. And in this video, we will look at all different types of colloids that there can be. And in this video, we will look at many examples of colloids that we see around us. Alright, so in order to understand different types of colloids, we need to understand the components of colloids. What makes up a colloid? And turns out there are two components. There is dispersing phase, there is dispersing medium. Dispersing phase are the solute-like particles. Solute-like particles that are dispersed in the dispersing medium. And dispersing medium is a component in which the dispersing phase is suspended. This is the component in which the dispersing phase is suspended. Now colloids, they are classified according to the state, solid, liquid and gas of both the dispersing phase and dispersing medium. So let's have a look at different types of colloids now. To begin with, let's say our dispersing phase is liquid. So we have the solute-like particles that are dispersed in the medium are liquid, and let's say the dispersing medium itself is a gas. This is the case when we see fog or mist or even clouds. And this type of colloid is called an aerosol. This type of colloid is called an aerosol. Examples are fog, you have mist, you have clouds. Now let's take the dispersing phase as solid. So the solute-like particles are solid and dispersing medium is gas. In this case, what you get is smoke. You get smoke or exhaust fumes coming out from trains or cars. And this type of colloid is also called an aerosol. So you have examples like smoke or exhaust, automobile exhaust, the exhaust fumes. Now let's take the dispersed phase as gas. So you have gas-like solute particles and dispersing medium is liquid. In this case, what you get is something like a shaving cream. And this type of colloid is called foam. This is foam. Example is a shaving cream. Now let's take the dispersing phase as liquid and dispersing medium as liquid. Example of this would be milk. Milk is an example of this, and this type of colloid is called an emulsion. So milk is an emulsion. One more example can be face cream. Face cream can be some other example. Now let's take dispersing phase as solid. This is solid, and dispersing medium as liquid. Example of this can be mud, and this type of colloid is called a sol. It's called SOL, sol. Example is mud. Now let's take dispersing phase as gas and dispersing medium as solid. In this case, you can think about what can you get in this case. So the solute-like particles, they are really gas, so there can be many air spaces, and dispersing medium is a solid, so there can be many air spaces in between a solid. What kind of a substance can this be? So turns out this is a sponge, right? You have these air spaces in between all the solid over here, and this is the type is really called a foam. And you have examples like sponge, even rubber. Rubber is also an example. Now let's continue, and now the dispersing phase is liquid. This is now liquid, and dispersing medium is a solid. Here you can get substances like butter or jelly, and this is called a gel. You can get butter, you can get jelly. Finally, let's take the dispersing phase as solid and dispersing medium as solid. So what you get in this case is very interesting. You get something like a gemstone. You get a gemstone. So you have solid solute like particles suspended in a solid medium. What you get are gemstones. And the type of colloid is called a solid sol. Solid sol. You had mud under sol as well when the dispersing medium was liquid, because mud is slightly watery, right? Alright, so these are all different types of colloids that you can see around you.
Now we're going to do some questions, practices, like which of the following is an emulsion? Which of the following is an emulsion? Choose one answer. Face cream, milk of magnesia, saving cream, etc. Which of the following is an emulsion? Choose one answer. Face cream, milk of magnesia, saving cream, etc. Sorry for the noise. I'm back now. Now let's do let's do the questions. Which of the following is an emulsion? Face cream, milk of magnesium, saving cream. Emulsion means first you have to find out if any word we can't understand, then you have to search it. Emulsion means what? It's a mixture of two liquids mixture. Okay, face cream, two liquids, yes. Milk of magnesia, saving cream will be not. I think milk of magnesia is the two liquid. Give it another try. No, this is not a. So milk example, make fat droplets, mixed water, no. Creams and ocean oil mixed with water, no. Mayonnaise, vinegar. So usually emulsion is like a soap or egg yolks. So saving cream will be the answer. Oh shit, face cream is the answer. How? Now they are giving the answer. Face cream is an emulsion because it contains two immiscible liquids, oil and water. Okay, oil and water, that's why, where one liquid is dispersed as tiny droplets in the other. Milk of magnesia is an example of sol. Saving cream example of foam. Okay. To identify non-homogeneous mixture. Non-homogeneous, homogeneous, heterogeneous. Okay, non-homogeneous means heterogeneous. Milk. Milk, all that apply these two. Now, the particles of the given mixture are visible to the naked eye, so it will be suspension. Which of the following can scatter a beam visible light? Muddy pond water, paint, and aqua solution of sugar. Which of the following can scatter a beam of visible light? Visible light. Paint. Paint can do that. Paint can do that. Yes, paint can do that. Muddy and paint. Yeah, both are right. Muddy powder is a suspension. The suspension particles are big enough to scatter visible light. Paint is a colloidal solution that dispersed particle is. So last, which of the following is a solid sol? Bronze, sponge, colored gemstone. Now, solid sol. Bronze, sponge, I guess. Colored. No, it's not. Then it will be this colored gemstone. Why? Because colored gemstone as solid sol, because tiny solid particles are dispersed uniformly in solid medium. So an example of foam. Okay, bronze is not colloid. It is an example of solid solution, or it is a colored gemstone. Colored gemstones are solid sols because tiny solid particles are dispersed uniformly in solid medium. Okay, so threes are correct. Now quiz 1. Quiz on 10 minutes, 5 questions will be here. So 10% acid added to 100 gram water of foam as aqueous solution. Calculate the mass percent of HCl solution. Okay, 10 gram HCl is added to 100 gram water to the foam as aqueous. Calculate the mass percent of HCl solution. It will be 10%, right? First try in ourselves, then we'll check. Water to form an aqueous solution. It will be 10, but this is not the right answer. Then we will find how to calculate it. So if it is not the right answer, then we'll try. Then we will try. We'll ask GPT for that. How to find. So explain. So mass and tells us how much. So mass equal to mass of solute by mass of solution. Okay. Oh, so here mass of solute by mass of solution. So mass percent equals to mass of solute by mass of solution into 100. So what is the mass of solute here? 10 HCl, right? And mass of solution is 100. Why 100? Because they are saying that added to 100 gram of water, but no 100, it's 110. Why? Because mass of solution they are asking, not solvent. If they are asking solvent, then we'll use 100, but here they are asking solution asking, then we'll use 110 into 100. Let's cut that 10. Now we have 10 is 100 divided 11. Now calculator. Yes, it will be around 0.11, I guess. No, 9.090. Yes, That's right. Now which of the following is a homogeneous mixture? Here says homogeneous mixture, there it will be solution. Next, 1 gram of glucose is added to 50 ml water to form an aqueous solution. Calculate the mass slash volume percent of the glucose solution. The negligible change in the volume here. Okay. So first we have to find out the formula. So what is the formula here? We have to first, what is the formula here? Formula. So mass volume percent. So mass by volume equal to mass of solid by mass of solution into 100. Same formula, bro. Mass of percent and mass of volume, same formula, no changes. So if here is no changes, then I have to convert ml to gram, right? It is in ml, so I have to convert it to gram. So if you need to convert it to gram, so 50 ml, right? 50 ml, if we convert it to ml to ml to ml to gram, right? If we have to convert it, then we have to use, so it's going up, then we have to use 50 divided by to 0.05 gram. Now we'll be using what it is, 50 ml 1 gram glucose. So 0 mass percent equals to no mass percent equal to no solute divided by mass of solution. Mass of solute is what? Glucose. How many glucose? 1 gram of glucose. 1 gram of glucose. 0.01 gram. It's something showing something fishy because of ml and this. First learn here. So mass of glucose 10 gram and volume solution 200 ml. You don't have to change it. You can use it as it is. Okay. The answer will be in percentage. Okay, I don't have to change it. So 1 gram glucose by 50. 1 gram glucose by 50 ml. 50 ml. That what they said. 200 ml. 200, use 200 directly. Don't need to change anything. So 50 into 100. 1 2, so the answer will be 2. Percent is 2. Yeah, simple as that. A given mixture has a particle size less than 1 mm in diameter, and why it's a solution, bro. So 10 gram CSOH is added enough water form 110 gram solution. Okay, added to enough water to form 100 grams. So if the density of solution is 1.1 gram per ml, calculate the mass volume percent of the CSOH. Oh, mass volume percent of CSOH. 10 grams is added to enough water to form 110 gram solution. It's given. The density of the solution is 1.1 gram ml. Calculate the mass and volume. So here is new thing is given, density. So we will first ask density. How to calculate density? What will be the formula here? The mass volume percent. You will use mass volume per percent. This is I know. The density equal to mass by volume. General method density, assume 100 gram solution. Standard method is instance 100 gram by 1. Find the volume density. 100 by 1.1, then we will get 90. That what we will get in ml. Then we use it a mass. So first we to convert density. First we need to get the volume. Because volume, why volume? Because here there are enough water. Not they are saying they aren't. they are not revealing the water percentage or water ml. So we have to find out the ml because the density is given. So 1.1 gram by 1 gram by no, yes. So if we say 100 gram of water, there is assume, we have to assume here like that. We have to assume 100 gram of water, sorry, 100 ml of water. Then density is given 100 divided by 1.1. Now volume equal to, now calculate that. 100 divided by 1.1, so we'll get 90.90 ml. So this is the volume of water. Now you get the volume. Now you know mass equals to how much that solute, 10 gram. 10 gram divided by what they are giving, the form of solution, 100 gram solution. So 100 gram solution is given, so why we use the water, why we need the water here? 110 gram into 100, why we need that? Let's take and see. 100 divided by 11, it's the same answer that previous one, 9.09. Let's see if answer is right or not. Yes, it's right. No, it's not right. It's not right because, so it's not right. I knew it. Because if the density of the solution is this, calculate the mass volume percent of CSOH. Mass volume percent. So what we find out here, this, we have to use this. But this is the volume, right? Why, how we use it? Volume and density. So what volume we get? Oh, okay, we will use it here. Not that, not this volume. We will use it here. So 10 divided by 90.90 into 100. Got that now? Yes, yes. Now calculate it. So if you take 1000 divided by 90.90, then you will get 11.00. So answer is 11 point. There you go. Show the answer then. 10%, but when I am using 10, you are saying that wrong. How it is 10%? First they find out the 1.1 equal to 110. 110, I did the same. The solution equal to 110 by 1.1. Hundred ml. Why 100 ml? It's saying that it is 100 ml. 110 divided by 110 divided by 1.1 is 100. Oh, I think I did a mistake here because I assumed something, right? Assume 100 ml. I don't have to assume here because 110 given ml or something given. 110 gram solution is given. So I have to use that. So I did the mistake there. So the question says that you have 110 gram of solution, right? So I have to use it. So like density equals to 1.1 density, right? 1.1 density equals to 110 gram but a V volume. We have to find out the volume. So now V equals to, we can say 110 divided by 1.1. We will find out 100 ml. Now use this 100 ml. Now we can use that 10 divided by 100. into 100. 100 cancel out and 10 remaining 10, so 10 is the answer. So that is how it's we done. Now what? Evaporation. We'll
In
be
other
learning
videos, we
evaporation.
saw how to separate solid from a liquid, particularly a solid which is not soluble in a liquid.
Okay.
So it formed a heterogeneous mixture.
Okay.
In this video, we will see how to separate a solid which is dissolved in a liquid. So in this case, this solid over here, this is really soluble. And when this solid dissolves in a liquid, it forms a solution. And you can take an example like salt dissolved in water or sugar dissolved in water. Either of that, both of them are soluble in water. Now, if I ask you to separate solid from liquid now when it forms a solution, when a solute or the solid is dissolved in liquid, how will you do that?
Yeah.
Turns out there are two methods. One method is called evaporation, and the second method is called crystallization. So we will look at evaporation in this video. Now, in order to separate the dissolved solid from water in this case, and let's be specific, let's take salt and water. What we can do is we can take an evaporating dish, which can look like this, and we can keep it on tripod stand. This right here is a tripod stand, and then heat it slowly from a Bunsen burner or a candle. So you have this solution in the evaporating dish, solution that is kept like this. So when you start heating the solution, the water in the solution, it starts evaporating, starts turning into water vapor, right? And when the entire water has been evaporated, all that is left behind is the solute or the solid or salt in this case, and crystals of such salt are obtained. Crystals of such salt are obtained in the evaporating dish. So that is how we can separate the dissolved solid from liquid. Now there is one advantage to this method, that is that this is a very simple method. It does not require complicated equipment. You can just have a dish and some heat source, a candle or a Bunsen burner.
Yeah.
But one disadvantage is that sometimes the solute can undergo thermal decomposition. It can undergo thermal decomposition. So what that means is basically the solid breaks down into two or more than two new chemical substances. So for instance, if you have some vitamins or minerals dissolved in water and you just need pure vitamins and minerals, maybe this method is not the best way to go, because those vitamins or minerals can undergo thermal decomposition. They can break down to form two new chemical substances. So this method is not useful for all types of solutions, but it is useful for some of them. For such other types of solutions, we can use the method of crystallization, and we will learn about that in some other videos. Now this method of evaporation, this method is also useful for farmers. So farmers usually collect seawater, and the heat from the sun evaporates the water from this solution, which only leaves behind crystals of salt. That is how salt can be obtained from seawater.
Okay.
So there you go. Evaporation helps you separate dissolved solids into liquids, but not all types of solids that are soluble in liquids.
So they are saying in this video evaporation, how evaporation can help us to find out the solute. Like if I adding in a glass of water 1 spoon of salt or sugar, then how can we separate sugar and salt with physical way? Physical means how can we do that using evaporation means if you can use a Bunsen burner or something else, fire, using a Bunsen burner or some fire, and use that glass of water and take it to the above fire and get the evaporation. After the evaporation done, the water will convert to gas, and the remaining things will be the salt or sugar. That's called evaporation. Now next.
Have you ever wondered why vodka is such a strong alcoholic drink compared to other drinks?
Okay.
That's because they use a process known as distillation once or even multiple times to increase the concentration of ethanol in the drink. Today, we will explore how distillation works and understand its significance. This is an experiment you can conduct in your chemistry lab, so let's examine the setup. First, in green, we have the distilling flask, which serves as the container for the mixture of compounds we aim to separate.
Okay.
Next, in orange, is the oil bath used for heating. Oil is preferred because it does not evaporate at high temperatures and helps maintain a consistent temperature throughout the process. Positioned above, in red, is the thermometer, essential for monitoring the temperature at which different compounds reach their boiling points. The
Okay.
condenser, marked in yellow, operates by utilizing a continuous flow of water that cycles in and out, helping to regulate its temperature and keep it cool during the process. The reason behind this is that the condenser needs cooling because distillation involves a series of vaporizations and condensations. At
Okay.
the beginning of the process, when the liquid in the distilling flask is heated, it transforms, changing from its liquid state into vapor as it absorbs heat. Then, due to the low temperature of the condenser, the vapor condenses back into a liquid and eventually collects in the receiving flask, which is shown in pink. This part also needs to be maintained at
Wait. Wait a minute. I have to go to washroom. I'm coming in 2 minutes. So where we are studying, right? So here.
At a low temperature. I have marked the ice bath in blue, kept cold, or even multiple times to increase the concentration of ethanol in the drink. Today, we will explore how distillation works and understand its significance. This
Okay.
is an experiment you can conduct in your chemistry lab, so let's examine the setup. First, in green, we have the distilling flask, which serves as the container for the mixture of compounds we aim to separate.
Okay.
Next, in orange, is the oil bath used for heating. Oil is preferred because it does not evaporate at high temperatures and helps maintain a consistent temperature throughout the process.
Okay.
Positioned above in red is the thermometer,
Okay.
essential for monitoring the temperature at which different compounds reach their boiling points.
Okay.
The condenser marked in yellow operates by utilizing a continuous flow of water that cycles in and out, helping to regulate its temperature and keep it cool during the process. The reason behind this is that the condenser needs cooling because distillation involves a series of vaporizations and condensations. At the beginning of the process, when the liquid in the distilling flask is heated, it transforms, changing from its liquid state into vapor as it absorbs heat. Then, due to the low temperature of the condenser, the vapor condenses back into a liquid and eventually collects in the receiving flask, which is shown in pink. This part also needs to be maintained at a low temperature. I have marked the ice bath in blue, kept cold for the same purpose as the previous component. The goal is to keep the setup's entire right side cool, allowing the liquid to condense back into its pure form. One more
Okay.
important component remains unlabeled, the vacuum adapter, which helps regulate pressure during the process. You might wonder why a vacuum is necessary for distillation. Wouldn't heating the liquid to a high temperature be sufficient to convert it into a gas? In some cases, no. Certain compounds possess extremely high boiling points, making standard distillation difficult. If the boiling point is too high, distillation becomes difficult.
Okay.
Lowering the system's pressure makes it easier to vaporize substances. At lower pressure, the force on the liquid is reduced, making it easier for the liquid to vaporize and transition into the gas phase.
Okay.
This allows distillation to occur more efficiently at lower temperatures. Let's consider a two-component mixture as an example. First, we have hexane, which I will represent in the flask. The second component is toluene, which has a higher boiling point due to its aromatic ring structure, making it more stable and less volatile. I will also display it in the flask. How can we keep track of what's happening during a distillation process? To track distillation, we typically create a temperature versus time graph, with temperature on the y-axis and time on the x-axis. The first thing that happens is the system heats up, causing the temperature to gradually rise. As you approach hexane's boiling point, around 68 degrees Celsius, a plateau starts forming. But why does this plateau occur? Let's quickly review what happens during a phase change. During this process, the temperature remains constant. Here, you will observe hexane transitioning from liquid to gas, undergoing vaporization as it moves upward. You will see the temperature recorded on the thermometer, and the vapor will condense back into liquid as it reaches the cooler side of the setup.
Okay.
At that point, you will begin collecting the drops of hexane. What happens next after gathering the contents in the flask? Once again, you will notice a temperature increase. Switch out your receiving flask at this point. You will see me change the color of the flask to indicate that this is a fresh flask, now used to collect pure toluene. At this point, the toluene reaches a temperature of 110 degrees, and you will observe a plateau. This plateau indicates the toluene is changing from liquid to gas, then condensing back to liquid.
Okay.
The condensed toluene drips into the new flask, ready to be collected in its pure form. In the end, we've successfully collected two separate flasks, one containing toluene and the other containing hexane. As a result, we were able to complete a successful distillation. Now, what if we had a three-component mixture instead? This process works similarly to a two-component mixture. However, you will observe more plateaus in the temperature versus time graph due to additional components. I will draw this graph on the side to illustrate. The first compound here is acetone, which looks like this. Next is cyclohexane, with a slightly higher boiling point than acetone. Finally, we have acetic acid, the third component. Acetic acid has a higher boiling point than the other compounds because it forms hydrogen bonds. These additional forces make it harder to separate the acetic acid molecules and transition them into the gas phase. Again, let's look at our graph. To understand, at first, you'll notice a slight temperature increase as you heat the flask. Once the temperature reaches 56 degrees, you will observe a plateau, indicating that acetone is vaporizing and then condensing. The temperature will continue rising until it reaches 81 degrees, where you will observe another plateau. This represents cyclohexane vaporizing and condensing as it transitions through phases. Finally, you'll notice another temperature increase, allowing you to collect acetic acid. Now, let's move to our final example and answer. How do they make vodka and other alcoholic drinks so strong? To produce strong alcoholic drinks, this type of distillation is typically used. The boiling points of ethanol and water are relatively close, with only a 27 degrees Celsius difference, making the distillation more challenging. Do you think this will impact the distillation process? Ideally, in your temperature versus time graph, you'd want to see a pattern similar to what we've observed in previous examples. Ideally, the graph shows a steady temperature rise, then a plateau at 78 degrees for ethanol vaporization, followed by a sharp increase and another plateau at 100 degrees for water vaporization. You might notice an initial increase at the beginning, but instead of a plateau, you get a slope. This creates an issue because it indicates both ethanol and water evaporate simultaneously, making separation harder. Previously, you might have been able to separate pure ethanol and pure water clearly. However, in this case, they mix together, creating a combined mixture shown by the purple line. Anything you see between these 2 points isn't really pure ethanol or pure water.
Okay.
It's mixture of the two. If you're still getting a mixture, it means the alcohol isn't strong enough yet. How can we solve this? One solution is to distill the compound again, hoping to further separate ethanol and water to increase alcohol concentration. If you're still getting a mixture, the alcohol isn't strong enough yet. How can we solve this? One solution is to distill the compound again, hoping to further separate ethanol and water to increase alcohol concentration. If you kept distilling it over and over, you might eventually get what you had hoped for, initially that ideal blue and pink separation. However, performing a simple distillation multiple times can be very time consuming. Is there a more efficient method we can use instead? In fact, another setup allows multiple distillations simultaneously. This method, called fractional distillation, helps separate components more effectively. If you compare the picture on the right with the one on the left, the only difference is the addition of a fractionating column.
Okay, yeah.
The fractionating column can be filled with various materials, such as beads, glass rings, or other substances which help enhance the separation process. For fun, I have filled it with stars.
Okay.
As you can see, the goal is to fill the column completely. And how does that affect what goes on during distillation? If you have two compounds represented by purple in this setup, instead of the vaporizing once and condensing again, the process becomes more intricate. The vapor rises, evaporates, and may condense on one of the stages in the column, enhancing separation. From there, it continues to rise, evaporate, and repeatedly condense, further refining the separation process. As the vapor travels upward through the packing material, it undergoes multiple cycles of vaporization and condensation. Each time it condenses, the components separate better. By the time it reaches the receiving packing material, which help enhance the separation process.
How?
For fun, I have filled it with stars. As you can see, the goal is to fill the column completely. And how does that affect what goes on during distillation? If you have two compounds represented by purple in this setup, instead of the vaporizing once and condensing again, the process becomes more intricate. The vapor rises, evaporates, and may condense on one of the stages in the column, enhancing separation. From there, it continues to rise, evaporate, and repeatedly condense, further refining the separation process. As the vapor travels upward through the packing material, it undergoes multiple cycles of vaporization and condensation. Each
Okay.
time it condenses, the components separate better. By the time it reaches the receiving flask,
Hmm.
the substance is much purer, as
Okay.
repeated cycles refine it beyond what a single distillation could achieve. So, what we covered today. We discussed setting up a simple distillation
Hmm.
effective for separating compounds with a boiling point difference of over 25 to 30 degrees Celsius. We also covered fractional distillation,
Yeah.
ideal for separating compounds with smaller boiling point differences.
Now next video is filtration.
I have this glass of water with some sand dissolved in it, and I want to
Okay.
separate the sand from the water. Can I do that? But turns out there is a method to do the separation, to carry out the separation, and that method is called filtration.
Filtration.
Filtration is used to separate a solid from a liquid. And in this case, the solid particles, they are not dissolved in water. Filtration only works for such purposes when these solid particles are not dissolved in water. Now, how to carry out filtration? Let's have a look at this. So we can pour the mixture of sand and water onto this filter paper that you can see is fitted in a funnel, and I have something near the bottom of the funnel which can collect the water that will come out. So when I pour the mixture, the filter paper filters out the sand particles and lets the water pass through it, which is then collected in a container at the bottom, and you can see that in front of you. Now this works
Oh.
because the filter paper has very small pores in it which can allow the water molecules, the water
Okay,
particles
okay.
to pass through it, but
Yeah.
it filters out, it does not allow the
The
bigger
sand
solid
particles.
sand particles to
Yes,
pass
yes.
through it. So
Yeah.
all the sand is collected in the filter paper, and
And
then you
the-
get clearer, much clearer water.
Yes.
It might still have very small sand particles present in it, but
Yeah.
the majority of the sand particles have been filtered out. So now
Oh.
let's have a look at the diagram. This over here, this you can see that this is a mixture, a mixture of the solid, mixture of solid and liquid. It could be anything. It could be chalk in water. Even chalk does not dissolve in water, right? And when you pour this mixture onto this filter paper, this right here is the filter paper. It lets the water molecules to pass through it, which is then collected at the bottom, and that is called a filtrate. That is called filtrate. In
Filtrate.
this case, the filtrate is water. Whatever sand that is collected in the filter paper, that really is called residue.
Residue.
So this is sand in this case. All right, now this over here is filter. This is a funnel. So let me write that as well. This is a funnel, and this could be anything. Any you can collect the filtrate in any sort of container. It could be a conical flask, a beaker, or just a everyday usable container. So this is how filtration works. It is used to separate solid from liquids, and this is a kind of a physical separation. This is called a physical separation
Physical
because there is
separation,
no
because-
change in
In-
how the particles are arranged.
Yeah,
Nothing
yeah.
new is formed. You're just separating sand from water. No
Yes.
new substance is formed. You're just physically separating them. And this is how filtration works.
Okay. So filtration also done. Let's go to the next.
Have you ever hastily scribbled something down with a black pen on a piece of paper and then accidentally smudged the paper with water? Then,
No.
what do you remember seeing? What happens is that you might see the black ink start to smudge and see some colors that are not black at all, maybe
Yeah.
some dark blues, some dark purples, and even hints of green or red. But
Yeah.
why is this happening scientifically? This is because black dye is actually made out of a bunch of different other dyes and different components. What you've just witnessed is called paper chromatography, a technique to separate ink into its component dyes. Chromatography involves taking a mixture and using a solid or liquid to separate it into its different parts based on their chemical properties. While there are many chromatographies, such as paper, gas, and liquid chromatography, they all rely on a mobile phase and a stationary phase to achieve separation. Let's see how paper chromatography works, since this is the simplest kind and a great way to see separation in action. In
Okay.
paper chromatography, the stationary phase is the paper which absorbs the solvent and helps separate the ink. Here's your piece of paper Draw a small line at the bottom and place a dot for your sample. This marks the starting position for the ink before the solvent moves upward, separating its components. To understand paper chromatography, you will need a beaker. The beaker
Okay.
is where the paper will be inserted and will come in contact with the solvent. Next, prepare a beaker or suitable container with a small amount of solvent at the bottom.
Okay.
Add your mobile phase, which can be any organic solvent. After that, pour in a small amount of solvent, ensuring the level stays below the sample spot to prevent direct dissolution and allow capillary action to carry the solvent upward. Again, not too much, because you don't want this to already be above the level of your spot, or else it will just all bleed together, ruining it. Now, you will place the paper into the container. Once you do that, the solvent will move upward, carrying different ink components based on their solubility and attraction to the paper. Now,
Okay.
you will observe that through capillary action, this pink solvent will travel up the piece of paper,
Paper.
carrying different dye components at varying speeds.
Hmm.
What you'll get is something that looks like this, with the spot remaining near the starting point as separation occurs, forming bands of color. As it moves upwards, it will separate the green spot into its colors, revealing the different pigments based on their solubility and interaction with the paper, creating a beautiful gradient effect. Let's see what happens at different time points as the separation progresses. At the
Okay.
first time point here, it separates into two distinct spots, indicating initial dye movement and separation. This actually implies that it's composed of two different components. If this were a very complex mixture, you could even see five or many
Five.
more spots appearing at different heights. If you
Okay.
wait even longer, this is what you'll see next as the solvent continues moving upward. You'll see the spots continue traveling farther up the plate, with the separation between them increasing. Ultimately, this demonstrates that the original green spot wasn't one compound, but two distinct compounds with different solubilities and affinities for the paper, allowing them to separate at different rates. And why do they separate this way? The blue spot traveled farther as it was strongly attracted to the pink solvent due to its solubility and weaker interaction with the paper, whereas the yellow spot didn't move quite as much,
Okay.
meaning it was more attracted to the paper due to stronger intermolecular forces. This competition between the stationary phase and the mobile phase you see drives the separation that occurs in all types of chromatography, allowing scientists to analyze it. So let's lay this information on a table. We have discussed how, in paper chromatography, the stationary phase is a solid that interacts with the sample components differently. The mobile phase is a kind of solvent. Separation occurs based on polarity, meaning how attracted each component is to the paper versus the solvent, depending on its chemical properties, molecular structure, and intermolecular forces. The
Okay.
next type of chromatography, almost identical to paper chromatography, is thin layer chromatography, TLC, which often
TLC.
uses coated glass. You'll see that all the spots in this table are the same. The main difference is that instead of having a piece of paper, you have a glass slide coated with a layer of silica gel, which serves as the stationary phase. This is a preparative tool used in organic chemistry for analyzing, identifying, and purifying compounds. To remind you that these two are related, I've drawn a small beaker containing either a plate or a piece of paper. The arrow indicates that the solvent is traveling upward through capillary action, carrying the sample components. The
Okay.
next kinds of chromatography we will see are column chromatography techniques. In this case, you have a column drawn here on the left. You fill it with packing material, add solvent, and load the sample to separate. The solvent moves downward, carrying components at varying rates. You'll find that as you keep adding more solvent, the mixture can separate into distinct bands, which will travel down the column at varying speeds based on their affinities. In basic column chromatography, the stationary phase is silica gel, while the mobile phase is an organic solvent, with separation occurring based on polarity, allowing different compounds to travel at varying speeds. In size exchange chromatography, your stationary phase is composed of beads with tiny pores in the middle. These pores allow smaller molecules to enter and slow down, while larger molecules pass through more quickly. So, in size exchange chromatography, these beads fill the column, tiny compounds pass through the pores while larger compounds navigate around them, resulting in size-based separation where smaller molecules elute later and larger molecules elute first, making this technique useful for protein purification. So what
Oh,
happens is that small compounds travel pretty far and fast, whereas large compounds take a longer time to come out the bottom. In ion exchange chromatography, the beads filling this column have some kind of charged group. Compounds with the same charge are repelled, while oppositely charged compounds bind tightly to the column, making them more reluctant to elute due to strong attraction to the stationary phase. This method is used for purifying nucleic acids, peptides, and charged biomolecules in research and industry.
okay.
Affinity chromatography is similar but usually relies on specific interactions, such as between an enzyme and a substrate, depending on recognition. This technique is used for purifying proteins and other biomolecules with precision, often employing ligands, antibodies, or metal ions. Things that bind tightly to the enzyme will primarily be the substrate, while everything else washes off the column. Later,
Yeah.
you can elute the bound compound by introducing a solution with stronger affinity, such as a competing ligand or high salt buffer disrupting interactions. This
Hmm.
method is widely used in biotechnology and research for purifying biomolecules.
Okay.
With high performance liquid chromatography,
HLPC.
formerly high pressure liquid chromatography, the process is essentially the same as basic column chromatography shown in yellow.
Hmm.
However, HPLC operates under high pressure, improving separation efficiency, resolution, and speed, making it widely used. But with HPLC, it's an advanced technique where you work with very small quantities, and the detector in the machine is more sensitive, ensuring accurate and reliable results. The last kind of chromatography is gas chromatography. This is different, where your stationary phase is a liquid, while your mobile phase is a carrier gas passing over the liquid, enabling separation based on volatility and interaction strength. What happens is you inject your sample and it travels through a coiled tube
Hmm.
into that box known as the gas chromatograph, where your compounds get separated. It is a fancy name for the equipment to run gas chromatography. Inside the chromatograph is a heated chamber through which an inert gas flows. The sample vaporizes and enters the gas flow onto the column. The most volatile compounds with lower boiling points travel faster, whereas
Okay.
substances with higher boiling points take longer to elute,
Longer time.
allowing effective separation based on thermal properties.
Okay.
And this is a separation method, is great when you have differences in boiling point. So now we have covered various types of chromatography, but each of these can be explored in greater detail.
So let's end it here. We'll continue the stream for next time. Let's goodbye. So today is for here basic of chromatography. Then in next stream we will finish this chapter methods of separate component. Okay, got it. So